Awful, yeah, I guess. I think I did all of them right for number 7.
Page 162. 163.
162,
So, I think I did all of them right, but I couldn't remember when, depending on which homomorphism, what it was going from, what was the beginning to the end, like what was the operation if I was
Okay,
supposed to use
so
multiplication.
whenever you're discussing homomorphism, there is a basic equality which you have to check.
Yeah,
Now, I think in all of your examples, you don't need to concern yourself with the function part. They're all functions.
Okay.
I look at it, but that's what I suspect is true. So the only thing which you have to check is when you have this map from one group to another group, you have to check that phi of AB is phi of A, phi of B. Okay? Now, you have to pay attention, because what is written here is just operation in this group.
Yeah, so first
if operation is here addition, so use addition, and so the same here. Okay, so that's the only thing which you have to check in order to show that a function is a homomorphism. So let's look at number 7, right? Number 7, I have a map R with this pesky cross to GL2, which is given by A goes to A100, right?
Yeah.
Okay.
So
operations here are cross. What is our cross? It's all reals without 0. Multiplication is operation here. So the question is, if you take AB, then of course it will go to AB 0011. Is it equal to image of A multiply image of B? If it is equal, it is satisfied. If not, it isn't. Is it?
yeah.
Homomorphism.
So I think like the one that I wasn't sure about
The last few, I think.
was like F, I think. I think it.
Okay, well, let me briefly look at that. Next is
Yeah.
R to GLR2. Now, when it's just R, it is relative to addition. But in GLR2, it's multiplication. So again, it will be a homomorphism.
Yeah.
Right? Okay. Next one, you're mapping 2 by 2 matrices into R by taking first corner. Now you have to realize what is the operation in M to R.
It says it's addition.
It is written even. It is addition now, but okay.
Oh, it's in the chapter.
Now, but why it is addition? Because multiplication there doesn't make sense. It's not a group under multiplication.
It's not just the invertible matrix.
It's not just invertible. Relative to addition, it's a group. Again, it's a homomorphism, no problem. Next is mapping D from GLR2 to multiplicative group, which is given by some formula. Is this a homomorphism? I hear one answer. Is it a homomorphism in D?
I didn't think this one was.
It isn't. It is not a homomorphism. Well, we can check it. Let's just check it, because that would be a good example. So we have, we're mapping A, B, C, D to AB, right?
Yeah.
Okay. So now if you take 2 matrices, now in order to have a, show, you can try to just choose an example, because in order to prove something, you have to prove in other cases. In order to disprove, it's enough to disprove for one case. But I don't know whether you want to do it.
Do you just use like that same one, or do you actually use different symbols?
You want to
well, yeah. Probably it's just easier for us not to think hard, but just to take second matrix. Its image will be, of course, alpha, beta, right? What? What's wrong?
Maybe we could stick with Arabic letters.
I don't.
Arabic letters I cannot
I don't
write.
think I've ever seen
It's
anybody
too hard
use
for me. But Greek letters is no problem.
No, I meant English letters.
That's, English letters is not Arabic letters.
I thought that's what we use as the Arabic alphabet.
No. We use Arabic numerals. What Arabic alphabet? Actually, it's not Arabic numerals, by the way, it's Indian numerals, which were brought by Arabs. But
that's what I was thinking.
that's what we're talking about here. So you want me to put numbers here? Okay.
No,
Well, let's
yeah.
multiply these two matrices. So I multiply this by what in each order. Say this first, this second. Alpha A plus beta C. That will be this one. Then it will be alpha B plus beta D and something here. I don't care. Right? And then it will go to this product. Alpha A plus beta C multiply alpha B plus beta D. And there is no reason for these two things to be equal. It may happen with some special choice, but typically these two things are completely different. Right? So that's it.
Well, as long as you can read it.
What? You don't know how to pronounce Greek letters?
I was just kidding.
I'm sure you know.
Slowly.
Well, you know some Greek words, you know. Do you know that you know some Greek words? You remember I was searching for some word and you volunteered the word for me?
I
Do you remember which one?
I
Do you
don't
remember which word you volunteered for me? No? Epiphany.
Oh, is that?
Of course it's a Greek word. Don't you see? Yeah. Don't you hear? It's a Greek word. It's a Greek word. Okay. Next one, mapping from GL to R to R. So GL to R operation is multiplication. And into R, their operation is addition. And what is this function? Has special name actually. It's called trace. Did they talk with you about what is a trace of a
you
matrix?
sum diagonal elements.
Sum of diagonal elements. So it's a trace. Now again, we check that it's not a homomorphism. Last one is a homomorphism because last mapping is from matrix to its determinant. Because this expression on the right and the last one in F is determinant. And I'm sure that when you were learning linear algebra, you were taught that determinant of product of matrices is product of determinants. Do you remember it? Determinant of AB, determinant of AB is determinant of A multiplied determinant of B. Didn't you have it? I'm sure.
Right, so the order of AB.
Well, it's notion for determinant. Sometimes determinant, you see, you don't like it, I can tell you that here.
I'm kidding.
That here and that here. Doesn't change.
I've just learned so much
But
notation in the past. just
trace won't work, and again, you can show it that it won't work. So let's check it. So this goes to A plus B, and I was stupid enough to erase it. This will go A plus D, right? This will go to alpha plus delta. So here I have to proceed because now this is the element I'm interested in. So it is gamma B plus delta D. Okay, and here I have if I take this sum, right, would it be equal to
the sum of those diagonals.
sum of this alpha A plus gamma B plus delta D? And again, if you look at it, there is no reason whatsoever for this equality. Okay. Now, if you feel unsure when there are some complicated formulas, you can look at them and try to arrive to an example. Because in order to disprove that the thing is homomorphism, it's enough for you to take two functions for which it won't work. Just two particular matrices, or whatever. So we're mapping from matrices to matrices, and you can try to experiment, you know. So for example, in this question, this phrase, you can take one matrix like this one, another matrix like this one. For example, you know, just fishing, on fishing expedition. What's the product? 1, 0, 0, 0, right? Okay. Next, Trace here, sum of diagonal elements is 0. Trace here is 0, right? Trace here is 1. Okay? Is this correct? No. That's it. It's not a homomorphism. And this is a big difference. If you want to prove something, you have to prove it for all possible cases. If you want to disprove something, it's enough to give one example. That's it. So, what?
But you had to multiply those matrices first and take the trace. Oh, that's it?
Yeah.
Oh.
That's exactly what I did.
Oh, I think it's just.
What?
I think it's just the opposite.
What is those?
Like, you know, if it's written that way,
Yes.
I think that's the opposite way. Is that right?
Yeah, that's the opposite.
Oh, okay.
This is AB.
Oh, okay.
Here is A, here is B.
Okay.
But it's the same thing.
Oh.
Yes. Okay. So number 7 is okay? What else?
Yeah.
16 in the same set? We have a finite group of even order. If we have a subgroup which is exactly half size, it must be normal. That's a simple problem. And we actually solved it in class when I was talking about alternating group. I told you alternating group is exactly half size, but here is the proof. In order to show that subgroup is normal, you have to show that left cosets and right cosets are the same, right? Agreed?
To show something's a normal.
Subgroup is normal if left cosets relative to this subgroup and right cosets are relative to the subgroup are the same, right? Here is my group G. Here is my group H. Size of this is, what is it? Let me put the same numbers as in your book. It has n over 2 elements. Well, I would write 2n and whatever. How many elements left here?
N over 2.
And all of this is group G. So, if this is H, if I take left coset of H, which is not H, what I will see? So this is H. If I take G, which is not an H, and consider GH, I will see something completely different, right? No one overlapping with H. What is the size of this? So it should be this, right? Right? Because I don't have any other place to put it, right? This is not overlapping with this, no intersection. Okay, wonderful. And what will happen if I take this? HG. Again, it should be elements which don't overlap with this. I don't have any other place to put them. So that's why they cancel.
Is it enough to prove?
If you write it carefully enough, that's certainly enough to prove. Because you have, if a group is a half size, how many left cosets you have? 2, right? If group is 1/10 of the size of a group, how many cosets you have? Just like in 10, right? Like in your video, which impressed me very much. Okay. Right? Because number of cosets is size of group divided by size of a subgroup. So this is very special case, because here you have just 2 cosets when it's half size. 2 left cosets, 2 right cosets. The point is that one of these cosets is the same, which is H itself. So you don't have any other possibility. Your right cosets also must be the same, and left cosets must be the same, which are different, because you just don't have a place to put them. Okay?
Oh, gosh.
Or you can think about it this way. Take H. You want to show that this is H, right? That's your question mark, right? If G is in H, it's as obvious, right?
Hmm.
So if G is not an H, right? Then that's the question. So you take G, multiply H, and then you say, oh, this set is G from which I delete H, right? Agreed?
Is that like G minus H?
Yeah, I for whatever reasons, I
Yeah.
like this set minus sign.
Right.
In your book, I think it's just this.
But it's different if the slash is going the other way, right? That's a factor group?
It would factor group.
Oh boy.
Okay, so let me put like in your book. And now, in other situations, I will have this inclusion always, right? If G is not in H, then the G multiply H is in G but not in H, so it belongs. But in this case, I have equality, just because of counting argument. Because size of this and size of this are the same. They are both n over 2. Okay. Okay? Now, because of that, if I multiply G minus H by G inverse, right, it should flip again. It must be equal to H. For which reason? This will be a little bit more involved. But anyway, if you take H and you multiply on the right by element which is not in H, right, then it goes here. So it tells me that if you take element from here and multiply it on the right by element not in H, it will go back. You understand? Because multiplication by element will exchange these two halves. This will go here, this one. And this is a direct analogy with what we discussed about permutations. Even permutation by even permutation is even. You can even try to do this if you want. You can try to do this also if you want. You can say, let's call all these elements even and these elements odd. Let's check that even multiply even is even. Certainly, it's a subgroup. Even multiply odd will be odd, because if I multiply element from subgroup to element, it's outside. Then I don't have any other choice. Then odd by odd must be even. You understand? Why? Because if I multiply even by odd, result is odd here, right? So if I multiply odd by odd, it must go to even, because if it's odd, I have a contradiction. Well, the easiest consideration is just this. If I consider left cossets, I have two of them, H and not H. If I have right cossets, I have two of them, H and not H, so they must cancel. Now, similar theorem would be correct, but it would be much more complicated if, say, size of G is divisible by 3 and not divisible by 2. It becomes more involved. So whenever you have smallest prime number by which your group is divisible, you have something similar. It becomes more complicated. For 2, it's this clear-cut simple case. So it's much easier than the previous discussion about representation of a group of size n as matrices. So which number was that? What is the next one you want me to talk about? Or you don't want me to talk about any?